But otherwise, I think we can just get ourselves started, and we can slowly let more people roll in as we get going. So welcome everybody, and thank you for joining today, this morning, this afternoon, this evening, wherever you're coming from. We're trying to cover quite a lot of different time zones here with this one today. And welcome to our Fluidit Water webinar, where we're going to be going through our drinking water modeling software, looking at mostly visualizations around the drinking water software. And very quickly, before I give an introduction to the two of us, I thought it'd be nice to run through the agenda that you can already see on the screen here. So for the next 5 or so minutes, we're going to be going through these introductions on ourselves, but also on the organization Fluidit. And then we're going to dive right into the good stuff. And please, as we're going, feel free to ask questions. Feel free to write in the chat as we're moving along. And of course, this is being recorded, so you can always have access to it afterwards and share it along with your colleagues. We'll be putting it up on our YouTube, and we'll be sure to share it with the rest of you. But really, the meat on the bone, the 25 minutes that we're going to be going through is going to be all about looking at data quality assurance. So when you start to bring in your network information systems and information from GIS into Fluidit Water, how are you going to be making sure that that data is of a high quality and making sure that there's no errors, really using visualization features to do these kind of background checks. Then more so just on actual visualization, how are we making sure that the visuals we're presenting are very, very insightful for those we want to display them to, be it our decision makers, colleagues, managers. And then finally, results and schematics. How can we, within the software, start to have these novel integrations where, as you're going to see later on, our software almost becomes like a PowerPoint or a Word document that you can really just plug and play to really simplify the process with your results and schematics. And then we've got some time for questions at the end. But please, if anything comes up, please put them in the chat as we go along. And very quickly, I am the long-haired gentleman in the top right corner there, at least I was. James Armour, the marketing coordinator here at Fluidit, and I've been working within the organization for a bit over a year, background in hydraulic modeling at university. And I am joined by Dr. Chris Baxter. Chris is here with us, and he's the president of Watson Solutions. He's got a little bit more experience than me, 25 years or 24 years more, so to say. And he's coming from his humble beginnings, I think he'd like to say, when he was one of the first people during his graduate program at the University of Alberta in Canada to actually start developing AI for drinking water networks. And from there, he's, of course, grown on to now doing the work that he's doing today with Watson Solutions. So welcome, Chris. And very quickly, before I hand over to Chris, I'm actually just going to talk a little bit, just one slide, about Fluidit as an organization, just to give those of you in the room who've not heard of us before a bit more background, and then I'll hand it over to him in just a second. But this photograph here is many of the team, at least the sort of founding group after the first year or two that we've been in existence. And actually, Fluidit was founded almost 6 years ago now, so it was the original 3 founders, and they are dotted around the crew just there. And really, they're all coming from a background of hydraulic modeling. So they'd all been working in the industry for over a decade, each of them, and had become frustrated with the current tools, or the tools that they were accessing at the time for their hydraulic modeling needs. And so decided to spin out and develop Fluidit and grow it into the organization we know today. And so initially, it was very much, how do we model drinking water networks? And it is expanded into also sewage networks, stormwater networks, and district energy networks. So any water moving through pipes, or also hydrology, overland flows with the stormwater management, that has all been brought into 4 different software lines. And today there's about more than 20 different countries that we're working in with existing clients. But today, of course, is all about drinking water. And I'm actually going to hand it over now to Chris, and he can take us away on his approach to visuals with Fluidit Water. So Chris, please take the floor.
Great, thanks, James. And while yes, the focus and the context today is on drinking water, the tools I'm going to share with you today apply across the board to all Fluidit software. So that is one of the nice things about Fluidit hydraulic modeling software, is there's a common interface for water, sewer, storm, and district energy systems. So all of the data visualization tools that I'm going to show you today apply equally to all of the other packages in our portfolio. So what we're looking at here is the Fluidit interface. We have a distribution system in the center of Helsinki displayed. And the first thing you'll notice is that our graphical user interface is quite lean. There's very few buttons, very few drop-down menus, and that's largely because most of the navigation in the software and access of information in the software is context-driven through left clicks or right clicks. Everything in the software is customizable. So the display that we're looking at right now is the distribution system, where pipes are represented by black lines and junctions are represented by black dots. I have a live web map as my background layer that's being provided by OpenStreetMaps. So if it takes a second or two for a background layer to refresh, it's because those tiles are being pulled in live over the internet. We also have our customer points showing up in pink. So Fluidit has as an option in the water software the ability to model your customers explicitly and then route their flows down to the junction as supported by the underlying EPANet algorithm. And as I mentioned, everything's customizable here. So if you're accustomed to seeing your pipes in blue instead of black, that's very easy to fix through what we call our drawing states. So what I have here is our default visualization. And if I want to change the color of the pipes, I simply click on the rendering for pipes and I can change its color to whatever I wish. And you can see I can change my colors to blue, to black, to green, whatever I wish in the background. And that's not an issue. And so everything, all labeling, all rendering, the size of the labels, the size of the lines, the size of the nodes is all customizable by the user, as is the overall look and feel of the interface. Okay. When crafting today's presentation, I thought, what are the typical data flows we have in a municipality or in a consulting firm when it comes to looking at data and the types of data that we want to visualize inside of a hydraulic model? And so what I thought I'd start with is about a little bit of an exercise in doing data validation with visualization tools. So a common approach when you bring in GIS data or data from another source into a hydraulic model is you may look at that data, perhaps in your GIS systems or perhaps in an Excel spreadsheet and do some sorting, ascending, sort, descending, looking for outliers, looking for data gaps. And that's not really an efficient way to do things, okay? Fluidit Water does have data validation tools, and I'll show you those in a few minutes. But I've created visualization tools within the software that are completely customizable to allow me to flag common errors that we would anticipate bringing in. So as many of you know, hydraulic modelers have a unique need for certain types of data. So even though your GIS data may be good, the reality is there's certain parameters that only hydraulic modelers care about. Things like a roughness coefficient, right? That's typically not going to be stored in a GIS database. And so we would anticipate when we bring in new GIS information that there may be, zero values or no values for roughness. So how do we flag that with visualization tools? What I'm going to do is I'm going to simulate the import of new data by going to a new scenario called GIS import April 2023. And we have this particular area here where I'm going to simulate the imported data. So this is new infrastructure that's been brought in. And I have my drawing states. So think of a drawing state as a saved thematic map where everything is customizable. And a model can have as many of those drawing states as you wish. So I have a folder here called Model Data Validation, and I've created data visualizers for flagging orphan nodes, for finding nodes that have zero or missing elevations. And I'm going to focus on this one, though, the pipe validation drawing state. So if I enable this drawing state, we see a few changes right away. So I've made the background layer disappear to add some clarity so I can zoom into the area and really see features of interest. And you'll note that there are different colors applied to the pipes. And these colors are meaningful. So these are my visual cues that there's something that needs to be investigated. So what I've done is I've created visualizers for roughness, diameter, and length issues in our hydraulic model. So I've said that if a roughness comes in with a value of under 80, and these are for Hayes and Williams C factors, we want that to be flagged by turning the pipe pink. If the pipe diameter is less than 50, and that would be in millimeters, we want that to be flagged in cyan. And this could help us find pipes that are, that have no diameter assigned, but also pipes that may have been entered. This happens often in North America where people may enter pipe diameters in inches, even though the model is in metric units. And so we might flag a 6-inch pipe here, which really should be a 150 millimeter pipe. And we also flag an issue that would cause potentially hydraulic model instabilities, and that's a pipe that has a length of less than 1 meter. Now, clearly by this rendering, the pipe is larger than 1 meter in diameter, but perhaps it came in with a 0 diameter. So I'm going to click on any one of these features. I'm going to click on a pipe here, and we see that this particular pipe, which was flagged for having a roughness value less than 80, does indeed have a roughness value of 0. Okay. Similarly, if we were to click this pipe, which is rendered for both diameter and roughness, it has a diameter of 6. So again, somebody probably entered 6 inches thinking that was the correct information. And in fact, we were expecting 150 millimeters. And we also have a roughness value of 0. Okay. So how do these visualizers actually work, and how do you set them up? Well, the software gives you the ability within a drawing state to add many visualizers. And a visualizer is how is a particular component or a particular label rendered. So if I were to take a look at this rendering for pipe diameter, for example, what I've done is I've created this rendering that will look for a filter. So the filter that I've applied is diameter less than 50, very simple. You basically type in the name of the field that you want to filter for, the value you want to filter, and then I've said I want to color code these in blue. Okay. I've also set the line thickness to be a line thickness of 3. Now, if we were to look at this other visualizer for roughness, the line thickness is slightly smaller at 2, and we basically used a filter of roughness less than 80 with a color code of pink. And what that allows us to do is see multiple visualizers on top of each other. So it's quite clear that this pipe has issues for both diameter with the cyan color and the roughness with pink. And what's really nice about the software is you can layer these visualizers on top of each other and make edits on the fly to your data, and the rendering will change on the fly. So if I were to take this one pipe that's being flagged for having a 0 length, I could also make its diameter 0 and its roughness 0. And if we look at that pipe now, we see that it's rendered, basically with all 3 validation visualizers. Another nice feature of Fluidit software is that we have the ability to do undo. So if I want to undo those changes, they disappear, right? Now once you flagged issues and you want to solve them, this is going beyond a little bit of the scope of the presentation, but we do have the ability to make changes to multiple components simultaneously. So I can just draw a box around all of these pipes that have been flagged with having 0 roughness, and I can go in here and assign the same roughness to all those pipes that have been flagged. And now we see the pink value has disappeared. I can go into my 2 blue pipes where the diameter was flagged as being 0, and change their diameter, and now we're just left with this one pipe. This one pipe, somebody overrode it with a custom length and put that length of 0. If I uncheck the custom length, the software will automatically compute it based on map units, and now we've solved all of our validation issues. So bringing those errors back, I can just do undo a couple of times and bring all those changes back. Okay. And I just wanted to point out that that's not the only way to validate your network. We do have built-in validation tools under a simulate menu item. I can go validate model. It's telling me this model is not valid for simulation. And we do have 2 out of those 3 validation errors showing up here. So I can click on the first one, which is invalid roughness, click on the second one, which is invalid length. Now, the one that didn't get flagged is the pipe diameter. And that is technically, from a hydraulic modeling perspective, it is possible to have a pipe of 6 millimeters. At least that doesn't make the hydraulic engine fail. So it's not a model error. It's just something that you want to be aware of. And so that's why having our own data validation tools with visualizers can really help identify gaps in your data. And these are all custom. You can create your own validation tools. A common one that we see our customers creating is one where you flag for elevations outside your normal ground elevation. So in Helsinki, which is at sea level, you might choose to create a visualizer for junctions that have an elevation less than 0 or above 100 meters, and those would be something you'd want to look at either in your GIS data because they might represent error conditions. So these do not come preloaded with the software, although for any of my customers, I'd be happy to provide these to you and show you how to create your own. But you can have as many of these validation tools built in as you wish. So what I'm going to do now is I'm going to go back to our default visualization for the entire network, and I'm going to change to a real working scenario, which is our existing model scenario. So now let's jump ahead. We have a model that's been imported, a model that's been created, a model that runs. One of the next things we like to do when we're exploring models with visualization tools is, kind of show me what we've got. So if I'm looking at this model for the first time, all I see is a system, and I don't really know how this system is made up. I don't know the diameters of the pipes. I don't know, where the flows are. I don't know where the pressure zone boundaries are. And this is another area where our visualization tools can help. So I've created a drawing state for pipe information. So if I want to start by looking at my pipes, if I double click the pipe information drawing state, the screen gets quite busy, perhaps at this scale, and I can change what's visible at which scale. But for the time being, I have a very simple valid drawing state on the screen that I can explore. And so what are we seeing in this particular drawing state? Well, this drawing state's been created, again, to remove the background layers to make the screen a little less busy. It's also rendering all the pipes according to the pressure zone that they're in. So Fluidit Water does have a tool for automatically delineating pressure zones. And so here we're looking at different zones within the network. So if I zoom into pipes that are in this lower zone 2, we can see the type of information that I've chosen to display on the pipe. Now you can display whatever you wish. You can have as many labels as you wish. You can make this screen truly busy. You can also have what we call our tool tips or pop-up tools, and these are customizable. So I've just moused over a pipe and I can get whichever information I'd like to about that particular pipe, and it shows up on mouse over. But what I've done in this particular drawing state is I've rendered my pipes according to their pressure zone. And if I blow up this pipe information drawing state to look at its individual components and click on the pipes, we'll see that the arrows on these pipes indicate the direction that the pipes were drawn. Okay, that's important because you can change the direction of the arrows so that they represent the prevailing direction of flow, the maximum flow, the net flow, or you can remove the arrows entirely. So in this case, I've chosen to make it the direction that the pipe was drawn because one of the labels that I've chosen to add to the pipes is the slope or the percent grade. And so if you're looking at a negative grade, that's derived based on looking at the upstream and the downstream nodes. So you need to know which one's the upstream and which one's the downstream, which is why I've chosen to use the arrows indicating the direction the pipe was drawn. Okay. So you can see that the coloring for the pipes is derived by coloring based on pressure zone. What about these labels? How were they created? So if I look at my labels, I have a diameter label. Okay? So what I've asked the software to do is for all pipes, I've asked you to label based on the field diameter. I've asked you to put a suffix on of millimeters. That's not required, but you can have it there, or you can remove it. And I've also asked it to display results with 2 decimal places. So I want you to display the value of diameter to a fixed number of decimal places, with that number being 0. So that gives us an integer value for all of our pipe diameters. Similarly, for the slope, I've asked the software to add a suffix of percent grade. You can change that on the fly. So if I want that to say percent slope, I can do that very easy. Okay. And now it says percent slope instead of percent grade. These labels can be changed. We can change the color. So if I don't want it to be black and I want it to stand out, I can make those labels pink. Okay. And all this can be done on the fly and can be changed by any user. And you can also copy and paste the drawing states, as we'll see in just a second, and use them as a starting point for a new drawing state, or just have multiple drawing states, one which is pink labels. Perhaps you have somebody who's colorblind and they want black labels. Somebody else wants a different color scheme. It's entirely up to you how you set these up. They're completely customizable. Okay. So what I'm going to show you right now is how do you actually take an existing drawing state and change its parameters to come up with a new drawing state. So I'm going to take this pipe information drawing state and I'm going to duplicate it. Okay. And so it creates an exact duplicate, and I'm going to activate that duplicate. So they're both called pipe information. I'm going to change this one. I'm going to create a rendering specific for trunk mains in my model. So I'm going to call it trunk mains. Okay. So I'm changing its information on the fly. I'm going to expand this. So I'm going to start changing this display. First thing I'm going to do is I'm going to get rid of those ugly pink labels. So I'm going to disable the slope labels. I'm going to disable the diameter labels. Okay. I'm going to now look at my pipes, and I'm going to remove the arrows. Okay. So clean the arrows up. Now I'm going to render, instead of rendering my pipes based on the pressure zone that they're in, I'm going to render them based on the diameter. I'm going to do it based on both the color and the thickness of the lines. So I can go through here, take my color code by zone, turn that off. And instead, I want to color based on whatever parameter I wish. So the software gives you the ability to render based on any parameter for any feature in the model. Okay, so they're all listed here very easily in alphabetical order. And I'm going to create, in this case, a rendering for diameter. And I'm going to scale the size also based on diameter. Okay. So now we end up with a display that looks a little, a little odd because some of our larger pipes are really, really thick. Well, we can change that. So I'm going to go to my pipes rendering and say that the starting line width on which all of the other scaling is based, we're going to make that a little bit smaller. And in playing around, I've determined that a value of 1.2 makes it clean where we could see the gaps, excuse me, between all of our different diameters in the model, right? So now when we're looking at this particular screen, we can see where our trunks are. This is the source of our system. We have a main coming through here, and this would be the main for lower zone 2. Now to clean this display up even more, if I want to focus just on visualizing the trunks, I can create a filter so that everything that's not a trunk main disappears. Now in this particular area of Helsinki, the trunks are going to be smaller than you might expect in North America for my colleagues that have joined in Canada. Distribution systems aren't designed for fire protection the same way that we have them in North America. So for the purposes of this model, I'm going to say that a trunk main is anything over, I'm going to make sure I spell it correctly, diameter greater than 100. And when I do that, all of the smaller pipes disappear. Okay. So now if you're presenting this to somebody else and they're perhaps not a hydraulic modeler, they might be wondering why all these dots are floating in midair, not connected to anything. Those are our junctions. So to clean up this particular display, I'm also just going to turn off my my junctions and make those disappear just by toggling them. So now what we're kind of left with is, valves, tanks, pumps, and our trunk mains. We can take this a step further. Perhaps you're only interested in looking at the trunk system in lower zone 2. One of the neat features about Fluidit software is we do have the ability to create what we call tags. So a tag is just any kind of value that you want to assign to a feature in the network. So you might want to create a tag for pressure zone, which I've done here. You can create a tag for year of installation. You can create a tag for material. You can create a QA/QC tag, which maybe means send back to my GIS department for error correction. In this case, I've kept it very simple. I've added a tag for just the pressure zone. And you can see where these tags exist. We do have the ability to interact with our model via component tables or attribute tables, as many people would call them. And we'd see here the pipes that are in lower zone 2 are tagged with lower zone 2. We're not going to spend time today looking at all the ways of exploring data. I'm focused exclusively on the visualization tools. But suffice it to say, you can interact. I can click on a pipe in here and say, show it to me on the map. I could be in the map and say, find this for me in the table. But for the purposes of today's presentation, what I'm going to show you is you can actually just type in the name of a tag and it will automatically filter objects on the display that create that tag. So I can right click on the map and I can say I can right click on the map and I can say filter components shown on the map and just say type in the name of the zone that I want to show, lower zone 2. And there you have it. I have just my trunk mains that are in that lower zone 2. And that selection applies even if I change drawing state. So if I go back to my default visualization, okay, which doesn't restrict based on diameter, now I've got all the pipes in pressure zone, lower zone 2 highlighted. And if I wanted to get the rest of my infrastructure back, I could right click and delete that expression. Okay. So far we've explored how to use data visualization tools for data validation, and we've also shown the power of our drawing states for exploring input data. I'm sure many of you are interested in looking at results presentation, because really I think of hydraulic modeling as the ability to tell stories. What does our system do? What happens if we make changes to it? And how do we present those results intelligibly to other people? So I've zoomed into my existing model. So I've selected my existing model scenario. And what I'm going to do here is I'm going to start looking at some of our output drawing states. So we have a drawing state here for pressure and velocity. Okay. So I'm going to zoom into this area of the network. And this actually happens to be a theme park in Helsinki. And my apologies to my Finnish colleagues, but it's pronounced, I believe, Linnanmäki. And if that's not correct, please correct me at the end of the presentation and I'll do better. But what's nice about having a theme park in the middle of your hydraulic model is it has very unique modeling characteristics, right? It does have a giant flume ride. It tends to suck up water in the in the middle of the night to prepare for the day ahead. And so we have characteristics and demand patterns that aren't representative of the rest of the system. So it does have some interesting hydraulics. And just to show you, we can right click anywhere on the display as well. and look at third-party tools for visualization. So I can look at Google Street View. I can find the address of the point I've looked at. But for this purpose, I'm just going to click on Bing Bird's Eye View, which will give us sort of a bird's eye view, a map of the system, so you can see how we've intelligently hidden our water tank in the middle of this theme park. And I think that's kind of interesting. Okay. But that is our water tank in the model. So the visualization I've created for pressure and velocity may not look exciting at first glance, but I'm going to show you some things that we do inside of Fluidit that I don't think you can replicate elsewhere, at least not very easily. So this particular rendering has all of my junctions color-coded based on their pressure in meters of head, and the thickness of the lines for my pipes is based on velocity. Now, again, I have black pipes. We can change those to blue or orange or whatever color you wish. But the feature that I think is particularly unique about Fluidit is that we can choose to turn labels on or off based on when a threshold is met. So we're not, when we look at a model, what do we think about for velocity? Well, we're concerned about, is the velocity in a pipe too fast, where we might be inducing scouring and effectively flushing our pipes when we're not intending to do so. So typically that threshold is what, 2.5 feet per second, or 0.7 meters per second, roughly. So what I've done in the software is I've created a label that will only show up when we're approaching scouring velocity. So I've said that if we ever encounter velocity greater than 0.5 meters per second, we want that label to show up on the pipe. So if I fast forward in time to about 2:30 in the morning, and I go through our time steps, these labels appear. Okay, so we have labels now. Certain pipes in our system are now have high flow and high velocity coming through them, and only those pipes are labeled. So instead of having a cluttered display with labels on every pipe, I've chosen just to highlight the pipes that meet a particular threshold, and I think that's unique to Fluidit. So if I were to open up this data validation and look at how that label was created, we have a label for what I've called large velocity. Again, I can choose the name for these. And so we are labeling based on instantaneous velocity in this case. You can also label based on max velocity, and I'll show you that how to do that in our next little demonstration. But the label is created very similar to how we did our input information. I said we want to label based on velocity. I want to add the suffix of meters per second. I want to have 2 decimal places. And I want to filter it so that the labels only show up when the result for instantaneous velocity is greater than 0.5. Okay? So if you wanted to make this a different threshold, you can change it on the fly. I can say 0.7, 0.3. If I were to change this to 0.1, for example, we'd have more pipes that get labeled throughout the network. Right? So you can make changes on the fly, and it really impacts the visualization of the tools, right? I think that's very powerful to be able to do that type of change on the fly, so that when you have questions about your models, we give you tools to answer those questions very quickly and very efficiently. So that's looking at results for one scenario. I guess before I move on to comparing scenarios, which is another nice feature, I could point out that we could easily just turn on labels for our points as well, and bring on our demand. So here now I've added labels for all of our demand points in terms of the pressure, as well as the junctions in the model. So you can add, remove labels, change display, change how things are rendered very easily inside the software just by clicking and double clicking. And you can even change the background layers, and we'll talk about that in a little bit longer. Okay. So what I'm going to do now is I'm going to go back to my default visualization, which is no visualization. I'm going to zoom into another area of the system, and we're going to simulate a very common hydraulic modeling exercise, which is we're going to add new infrastructure to our model, and we want to see how our existing system can handle it. So here's an area of the system that appears to already be built out in the real world, with multifamily residential, and we would presume it would connect to this portion of the system. So I'm going to fast forward to a 2030 max day scenario where this infrastructure is live. Okay, and so our big concern when we add new infrastructure, we'll just wait for the OpenStreetMap tiles to load. There we go. Is what happens to this area of the system? What happens to the pump that services this system? And how can we do comparisons? Now, in other hydraulic modeling software packages that I've had the ability to represent in the past, doing a visualization with comparison becomes quite onerous. In Fluidit, it's very simple. So I've created a drawing state here where we can do not just pressure and velocity, but pressure and velocity change. So if I double click and make this rendering active, what I'm showing here is the delta between the active scenario which is the 2030 max day scenario, and whatever other scenario I choose. In my case, if I were to look at these velocity changes, I've asked it to compare to the scenario existing model. So the scenario that's live is my 2030 max day scenario. It's highlighted here. And I've asked the software to compare the results back to the existing model, which is my 2023 model. So everything that we're rendering here is based on the delta between those two. So we are looking at rendering the pipes based on the velocity change, rendering the junctions based on the pressure change. Now, obviously, for the new infrastructure, the values here will be their max values because there is no comparison value for the existing scenario. So when you see a value here, that's 49.7 meters. So that is the value is basically the pressure at that node based because there is no value to compare it to. But in any case, we're concerned looking at these parts of the system, and I can see that we have some velocity changes throughout the system. We do have some minor pressure changes in the connecting area. And so, we can look at this and go, yeah, we can add this infrastructure to our system without much problem. We haven't induced any issues in the neighboring area to be concerned about. So I think that's quite powerful. I'd like to take this a step further, though, because looking at just a thematic map is nice, but what if you actually wanted to have charts and other information available at the same time? And for that, we have something that we call schematics. So we have a schematic created to explore how our system changes in 2030 with the addition of this new infrastructure. And it does rely partially on this thematic map, but it has other components added to it. So this is the 2030 operational changes schematic. So schematic could be comprised of whatever you wish. In this case, I've chosen to have a title. I've brought in a zoomed in view of the area of concern where we're adding new infrastructure with the same thematic mapping that we just showed you in the map view window. So I can go back and forth between map view window and the schematic. I've also added a graph showing what's happening at the pump station that feeds this area. So we can see the existing flow in that pump station in red and the flow coming out of the pump station when we add these new customers. So we see there's not a big issue. And we also look at the pump efficiency. So where is the pump operating on its pump curve in the future? So do we need to upgrade our pumps? Here we're still operating at peak efficiency, so we're not concerned. So you can create these schematics to tell the story that you want to tell. And I think that's really important in hydraulic modeling is you're trying to prove a hypothesis, you're trying to generate interest in a project or confirm that the work that you're proposing is going to be acceptable both to existing customers and to the new customers. And you can do that quite easily with schematics when layered on top of thematic maps. I'm going to show you a different schematic, which is looking at a different portion of our system. And this is going back to our water tower area. So that water tower we saw in the middle of the what is it? Sorry, I'm gonna close this one down. So the water tower that we saw in the middle of our theme park, what's going on at that particular location. So what I have rendered in front of me here, I'm just gonna put this. Sorry, just want to make sure you get the right one. There we go. Just waiting for this to refresh, but by opening and closing it refreshed fine. So what we have here is a thematic map, and this particular map is not assigned to a particular scenario. So which it means if I change scenarios, the map is going to update, as will all of the graphs in this schematic. So right now we're showing the existing model. So the model as it exists in 2023. And I'll show you how we change that in just a few seconds. But we have here is a thematic map looking at the water tower inside the theme park. We are looking at the tank level, the level in that tank at the current time step. And so we have this pictograph showing the actual level, as well as the level being pulled in. So the data is coming in here. This is what we call a value view figure. So we're pulling in the water level, as well as the total stored volume in the tank. We also have a plot showing up with the tank level over the course of the simulation, as well as the inflow to that tank. When you're looking at information like this, oftentimes you have to look at IDs and kind of correlate a map with an ID on a map with an ID in a chart. And you'll notice here that my presentation is completely devoid of IDs. You haven't seen ID numbering anywhere on the map. And while they're certainly supported, I think it's a lot cleaner if you don't have IDs on every junction and every pipe in the network. So what can I do if I was going to share this information with somebody else? Well, and they didn't know where the inlet to the tank was. And I just wanted to point that out. We could do something super simple, like just draw a dynamic arrow. I could say this trace applies to this line. And if I really wanted that line to stand out, I can make it pink, and I can make the thickness a little bit large. I can make the thickness a little bit larger. Maybe not that large, but there it is, right? So that's basically saying, this trace applies to that feature, which is really nice. Okay. And I can fast forward in time, right? And the tank level will change. And you can see I have a line that'll show me where I'm at in the simulation, and everything updates, right? So what's nice about these schematics is I can also duplicate them, right? So I can take this schematic and I can say I want to duplicate the schematic, and it's giving me the new one, water tower. I'm going to enable it. Okay, it looks identical to the other one because it's a duplicate. I'm going to change its name, and I'm going to change its name from water tower to water tower in 2030. When we have max flow conditions. So there it is. Now I can make the elements of this particular schematic choose data from a particular scenario. So right now it's based on whatever scenario is active, which is the existing model. I can tell the software that we want this map to update to be a specific scenario. So I want it to be showing me information from the 2030 max day scenario. And I could do the same for my chart. So if I go into my chart, I can say that the expressions that are on this chart, so I have two expressions, one for inflow, one for level. I can show where those are, and it's pulling in. See, it's pulling in tank level from the active scenario. I could say I wanted to instead pull from the 2030 max day scenario, and I could do the same for the tank inflow, 2030 max day. And when I press apply, okay. So now that's just shifted this plot to represent what's happening in 2030. And if you wanted to do a comparison, you don't have to be running multiple instances of Fluidit Water. You can do that comparison directly inside the software by just dragging that window wherever you wish. And so you can see a slightly different profile for inflow and level within the tank. One is for 2023, one is for 2030 max day. Okay? And this may look a little bit squished simply because I'm showing this to you on a 17-inch laptop. But if you had multiple screens, you can drag these on multiple screens. And I guess, sometimes you just need to create a report. Everything I'm showing you here, you would normally have to do outside of your hydraulic modeling software. I'm not aware of other software packages that give you this level of flexibility in creating things like schematics and complex drawing states. But sometimes you just want to, dump what you have over into, a Microsoft Office product. So I'm just going to select everything. I'm going to press Control C to copy. I'm going to go over to Word, press Control V, and you can use this as the basis of a report. So that wraps up my my overview of data visualization inside of Fluidit Water, which again applies to all of the tools in our Fluidit family. We do have some time for questions. I'm not sure if anything's shown up in the chat, James, that you want to feed. We also have some of our hydraulic modeling team on the call, and we can go into a deep dive on questions over the next 5 minutes that anybody may have. Of course, the presentation has been recorded. We'll be sharing that recording once we've edited out the first little bit, where it was just James and I greeting each other and talking about the weather. And if anybody wants to reach out, I think most of you can find me on LinkedIn or via my email that's going to be in the presentation as well. And we'd be happy to have conversations and follow up deep dive presentations with any of you.
Perfect, and thank you very much, Chris. That was great. That was great viewing, and I hope everyone in the webinar enjoyed it. I saw there was one question as we went through there about the establishing pipe libraries, and for those of you that might have missed it, we do already have stock pipe libraries inbuilt into the software, but you can indeed import your own material libraries. And
Yeah.
you can take this from Excel, or you can take it from other sources. Yeah, really, there's a lot of functionality there. And
yeah, that's correct. You can have your own custom pipe library, and we basically call it a material. And then instead of having to input roughness and diameter for your pipes, you can just select the material, and it'll automatically apply the right hydraulic criteria to those pipes. This particular model does not have one loaded. We do have a stock material set for Finland, but this particular demonstration model, which was designed for a North American audience, doesn't have the Finnish materials loaded.
And we've got a question about if you want to zoom in a little bit to some of the pipes, about the direction of the arrows on the pipes. and whether these are live and if they change directions following, is it pipe flows? Is it
Well, it
gradients?
depends. It depends on how the pipe is rendered, right? So as I pointed out earlier, so if let's just put an output drawing state in place here. So if my pipes are rendered, in this case, rendered by velocity, right? And so the arrow direction is indeed net flow direction, but I can actually make it the current direction. So did you see that one just change? So this particular one is now, so the theme now has been changed. So we're showing the direction at the current time step. Whereas I could change it here to my net flow, which means over the course of the day, which way does water flow? And it's this way. So you can do it both ways. You can have it be static because it's showing the direction that the pipe is digitized, or you can have it be based on instantaneous flow, which is current direction, or max flow or net flow conditions for the day.
Perfect. And I saw there was somebody typing there in the chat, Ardian, but perhaps you don't have a question for today. But as Chris mentioned, this is going to be recorded. It'll be up on our YouTube channel, or it was recorded. It'll be up on our YouTube channel, and we'll be sure to share it with you all tomorrow, if not later this week. And we'll be, oh, we've got another question just coming in here. So comparing different scenarios on schematics, Chris, if you want to dive down.
Yeah, so if I go down to, let's pick maybe in my water tower example. So we could certainly, instead of this, let's take, right now this particular graph is showing, one scenario, tank inflow and tank level. So say I want to look at tank inflow over two scenarios. First, let's get rid of this big, the big arrow, delete that. If I wanted to click on this pipe, I can go to the expressions that are actually part of this. So a variable one is tank level. So let's change, so that's for the 2030 max days. So let's make this one tank level as well. Okay, we can name it, I'll put this tank level 2023, right? We're to do this. So this is my existing model. So I have tank level 2023. I'll make this tank level 2030, right? So there we go. Water tower level, which is pressure from a hydraulic modeling perspective. Gonna go okay. So now we're showing we've created a schematic with tank level for 2023 and 2030. So yes, you can do multi scenarios. You can have 10 scenarios if you wish. You just add more variables to this chart.
For sure. And also alternately for those listening, you could zoom out even further and copy the graph and have multiple graphs on the one screen. But
correct. Yeah. So I can easily just create this. I can create this and just, copy and paste it and have another version of that graph, right?
Zoom out and do
so the beauty of
24,
schematics
64.
is that you can, your schematic is really a giant whiteboard that you can put whatever you want, wherever you want it. And you can lock certain elements to a particular scenario, certain elements to the base scenario, and certain ones that will change based on the scenario that's selected. So, I've been doing hydraulic modeling a long time, and I've represented different companies over my tenure, but I've never seen a software package that allows this level of flexibility. And we haven't even gotten into the ability to write your own custom scripts and do your own custom expressions and filters and things like that. Like if you're a power user of hydraulic modeling software, you'll appreciate all of that. But if you're somebody that doesn't like the frustration of copying and pasting out to third-party tools or creating graphs in Excel because you can't do what you want inside your hydraulic model, I'd really encourage you to have a deeper look at what we do at Fluidit.
Perfect. And lots of thanks coming through in the chat here, Chris. So thank you all for listening. And we know we just run over by a couple of minutes there, but we'll be sure
1
to share.
minute. That's pretty good.
It's perfect. It's perfect. But we'll be catching up again in the future, and we'll certainly share the next installment of our webinar series with those of you that want to dive in again. So thank you all very much. Good. Enjoy the day. Enjoy the evening. Hope it's sunny where you all are, and we'll hopefully see you all again sometime soon.
Thanks, everyone. Have a great day.